Okay, so here we go. Number 3 on worksheet 8.3. We just asked about C and D. So here's what we know. We've got this graph. It gives us the potential energy as a position of function for a 0.9 kilogram thing. It can only travel along an x-axis. Non-conservative forces are not involved, so our total energy is going to stay constant. It gives us the values here. So let's see. UA is 15 joules. UB is 35 joules. UC is 45 joules. The particle is released at x equals 4.5 meters. So, and at that point, it's got a velocity of 7 meters a second. And it's headed in the negative direction. So I'm going to put a little negative sign there, because that feels like it's probably important. So it's released from here, moving this way. Does that make sense? All right. Okay, so without sort of reading too much further, let's pause and kind of figure out what this all tells us. The reason you're given x is because that's going to allow us to find, well, you guys tell me, why were you given x? Okay, it's your start point, but there's something important about that specific number. Yeah, you can read the graph and find your potential energy, right? So my potential energy that I begin with is 15 joules, right? Okay? And I gave you the velocity, or they gave you the velocity, so you could find the kinetic energy, right? So 1/2 mv squared, so you're going to get 0.45 times 49, which gives you a number. 0.45 times 49 gives you, who wrote this? 22.05 joules. So it looks like my total mechanical energy is going to be, what, 37.05 joules? I'm sure you could probably just round that to 37 and be fine. But all right, everybody good up to there? Okay, so if we draw that in, it's going to be kind of like right here, right? Okay, so if I push this thing to the left, what would it do, you guys? It's going to make it up the hill, and it's going to get to a position of 0 and still be moving to the left. So I don't know what will happen after that because it doesn't tell me what happens when the position becomes negative. Okay? So my assumption is it just would go off to infinity. All right. So part C and D say, suppose instead it's pushed to the right. So that's the only thing that's going to change is the direction of motion. The fact that the velocity is positive won't change my kinetic energy, right? Does that make sense, you guys? Okay, so C, can the particle reach x equals 7 meters? What do you guys think? No. If so, what's its speed there? If it can't, what's the turning point? So this is the same thing I just did, right? You need to find the coordinates of that point. So I guess you can either use triangles, or you can write an equation for this line and find the value of x for which...
Okay, I had my kinetic energy was 220.
Oh, gotcha. Okay. All right. D, this is good. This is the first time we've talked about one of these today. It says D, says find the force on the particle as it begins to move to the right of x equals 5 meters. Find the force on the particle as it moves to the right of x equals 5. So it's asking for the force in here. What am I really asking you to do? Adam, what do you got? No. So you're close. It's calculusy, but it's not area. So I don't know. Anthony, I haven't talked to you yet.
The negative derivative.
Okay, yeah, it's the negative derivative. Okay, so that is worth, let's take a quick second and review that. So what we learned, you guys, was this, that, how do I want to write this? Your force is the negative derivative of the potential curve. Okay, so Evan, to your point, where the area becomes important, if this had been a force versus position curve, then That's when you take your integral. Cool? Make sense, you guys? Yeah. So notice the negative here, you guys, right? Because technically this integral gives you the work done by the force, which is actually the opposite of the change. I don't know if that's what you were going to say, Adam. I really should have had a delta there.
I was going to say, because the answer key says 30 newtons, so if it's the negative derivative...
Oh, do I not have the negative on there?
No.
Oh, it should totally be negative, so that's a mistake on my part. Yeah. Do you guys see why it should be negative?
It says in the negative.
Oh, it says in the negative direction. It says it.
Oh, got it.
Yeah, it doesn't use plus or minus, it uses words. Yeah.
Oh, on the answer key. Oh, I see. Okay. Gotcha. Good?
Yeah.
Okay. Evan, you good? All right. What else, you guys? Okay. So, I know you guys had asked for a little bit more practice on this. I don't know that I have a ton of time to come up with anything else on it at this point. Which I really feel like this hits most of what you need to know for conservation of energy. All right. So in my mind, this is a big idea, but honestly, this was on that last test, right?
Yep.
Okay. The biggest new thing from this is A, being able to work with these graphs, and B, understanding that as long as, at this point, keeping it simple, as long as your only forces are conservative, your total energy is going to be constant. Okay? I guess I should say, if they're non-conservative forces, but they don't do work. So I'm working on writing the final right now. My goal is to kind of hit, have sort of one question from each chapter.
You want me to write it for you?
You could. That would save me a ton of time.
I know exactly what's on.
So my brain just totally shut down.
Question 1, 30 points. Name.
Stop this. Okay.